Hello industry colleagues, I am from Laplace. Next I will present a report on the role of laser technology in N-type high-efficiency photovoltaic PV cells and share our achievements. The report will be divided into 4 sections: industry trends, efficiency, enhancement pathways, solutions, and Laplace introduction. Part 1. Industry trends. I will mainly introduce the mainstream solutions for the N-type battery technology roadmap and the application of laser technology within them. First, regarding the industry background, domestic demand for high-power module tenders is gradually increasing. Currently, the Chinese PV market's demand for high-power modules is showing a growth trend and has become the preferred choice for end customers. According to TrendForce data, in November 2025, tenders for modules over 570 W accounted for more than 60% of the scale, and demand for power ratings over 600 W and 700 W continues to rise. Leading companies such as Trina Solar, LONGi Green Energy, and Jinko Solar have achieved mass production of modules over 700 W and are continuously improving product performance through technological upgrades. In terminal projects, the application scale of modules over 700 W is gradually expanding. Their advantages of high power, high efficiency, and low levelized cost of electricity, LCOE, are driving the industry to transition from scale expansion to quality improvement. Overall, the current development model of the PV industry is shifting from extensive scale expansion to lean manufacturing driven by technological innovation. In terms of competition, it is shifting from homogenization and cost involution to achieving product premiums through differentiated technological paths. The increase in demand for high-power modules is the result of multiple factors, including policy support, technological progress, and improved economic viability. First, regarding policy and market environment, driven by the dual carbon goals, China's targets of carbon peaking by 2030 and carbon neutrality by 2060 are pushing PV to become a core track for energy transition. End customer demand for clean energy continues to grow, and higher power generation efficiency has become a key choice to meet large-scale energy needs. Regarding installation demand expansion, China's new PV installations in 2025 are expected to exceed 250 gigawatts, with centralized power stations accounting for over 40%. The high-power characteristics of modules can reduce the number of modules, lower initial project investment, increase power generation, and reduce balance of system (BOS) costs, meeting the cost reduction and efficiency enhancement requirements of large-scale installations. Regarding technological progress, N-type battery technology has matured. The conversion efficiency of TOPCon cells continues to improve, laying the foundation for high-power modules. The high bifaciality and low degradation rate of N-type modules further enhance power generation. The application of 210 mm large-size silicon wafers, along with standardization and promotion, optimizes module formats. While maintaining high power, it reduces module size and weight, improving installation convenience. Looking at the technology iteration path, N-type high-efficiency PV cells are an inevitable choice under the efficiency ceiling. N-type silicon, with its intrinsic advantages such as higher minority carrier lifetime and near-zero light-induced degradation, lays the material foundation for developing high-efficiency cells like TOPCon and BC back contact. The chart below shows the theoretical efficiency limits under different passivation technology routes. It can be seen that for early P-type PERC cells, the theoretical efficiency limit is 24.5%. The back surface recombination current density, J0, being greater than 200 FA cm squared is the main constraint on efficiency. In industrialization, as efficiency approaches the theoretical limit, the marginal cost of efficiency improvement is high, and capacity is gradually being phased out. For HJT, heterojunction, cells they use intrinsic amorphous silicon plus doped amorphous silicon for passivation. The main constraint on efficiency is high optical loss, with a theoretical efficiency limit of 28.1%. For TOPCon cell technology, if a double-sided tunneling oxide layer plus polysilicon layer passivation is used, the conversion efficiency upper limit can reach 28.7%. Therefore, N-TOPCon is currently the main force in industrialization, with a clear efficiency enhancement path. However, its main efficiency constraint is the inability to balance carrier transport and optics. If we transfer both the N-type and P-type structures of TOPCon to the back of the cell, we naturally transition to the BC route. Through the BC platform technology, optical absorption can be maximized, and the conversion efficiency upper limit can reach 29.1%, which can leverage advantages in the high-end market differentiation. Regarding industrialization pathways, in 2025, N-type TOPCon, with over 75% market share and mature cost-effectiveness, firmly holds the mainstream position. BC technology, with a share approaching 10% and higher efficiency, targets the high-end distributed market. According to statistics from the China Photovoltaic Industry Association, CPIA, from 2024 to 2030 regarding the market share of different battery technology routes, in the next 5 years, N-type TOPCon battery technology will occupy the mainstream position, while BC technology will also see rapid growth and large-scale expansion. Looking at the trend of production line investment costs for different battery types, due to first-mover advantages, TOPCon cells have lower initial equipment investment costs. For BC technology, the investment cost per GW in 2024 was about 300 million RMB GW. However, with the gradual localization and promotion of equipment and the maturity of the battery technology route, the investment cost per GW will also see a rapid decline. Overall, as core process equipment gradually completes localization and replaces iterative technologies, rapid cost reduction can be achieved for technology iterations. From the perspective of trends, laser technology has been deeply embedded in the development of N-type high-efficiency cells from the beginning. Its high precision, low damage, and controllability are key supports for meeting sub-micron precision processing requirements and driving the mature mass production of technologies like TOPCon and BC. Looking at the development path of laser technology, early TOPCon SE, selective emitter, technology used lasers to achieve local high temperatures for heavy doping in metallization areas. Moving to LICO, laser enhanced contact optimization technology, lasers play a role in carrier excitation. Under reverse voltage, high current density local hotspots are formed at the silver-silicon interface, promoting the formation of silver-silicon alloy junctions and reducing contact resistivity. In half-cut technology, local heating by laser and subsequent cooling jets create thermal stress gradients, achieving high-quality, non-destructive slicing through thermal stress cleavage. Currently, laser etching is widely used to achieve precise removal of local film layers via laser. Fundamentally, the N-type transition is a manufacturing revolution. Its success depends on the innovation of underlying tools like lasers that can achieve precision, flexibility, and low-damage processing. From the battery manufacturing route perspective, manufacturing precision is moving from the micron level to the sub-micron level, with unprecedented requirements for thermal damage and patterning precision. Laser technology has moved from optional to mandatory, becoming a key common process for achieving efficiency, enhancement, cost reduction, and mass production of N-type cells. Part 2. Efficiency Enhancement Pathways. I will take TOPCon polyfinger, TBC, as an example to detail its efficiency enhancement methods and the necessity of lasers within them. First, a brief introduction to the TOPCon battery technology route. The high efficiency of TOPCon cells stems from the core passivation contact structure of the tunneling oxide layer. Through the structural synergy of an ultra-thin silicon oxide layer and a doped polysilicon layer, it achieves excellent chemical passivation, long-term passivation, and carrier selective transport, thereby significantly reducing surface recombination velocity and improving open circuit voltage and conversion efficiency. The charts below show the structural cross-section of the tunneling oxide layer and its local energy band diagram. It can be seen that the band bending formed by the N+ poly layer and the potential barrier formed by the tunneling oxide layer can effectively create carrier selectivity, field effect passivation, increasing electron migration rate while suppressing hole migration rate. The ultra-thin oxide layer allows majority carriers, electrons, to tunnel through while blocking minority carrier hole recombination. This structure greatly reduces metal contact recombination current. From the analysis of efficiency gain, PV cell efficiency losses mainly come from two aspects: optical and electrical losses. In the conventional TOPCon battery technology route, although the backside uses a tunneling oxide layer plus a polysilicon layer for passivation, forming good passivation quality, the presence of the polysilicon layer causes significant parasitic absorption. In the relevant research below, it can be seen that when the polysilicon layer thickness is reduced from 125 nanometers to 90 nanometers, the external quantum efficiency, EQE, in the long-wave band increases. Correspondingly, the increase in long-wave reflectance and optical path enhancement factor corresponds to the reduction in parasitic absorption. From the free energy loss analysis of TOPCon, the recombination effect of the front surface boron diffusion layer accounts for more than half of the total free energy loss, making it the main constraint. Therefore, in early TOPCon battery route predictions, the main efficiency enhancement paths included reducing parasitic absorption via polyfinger, reducing metal-induced recombination via laser SE, reducing emitter recombination, specifically by adopting lightly doped, difficult-to-achieve, high sheet resistance profiles in non-contact area. In further battery routes, suppressing recombination at the front surface field and contact areas was introduced as a key strategy for improving battery performance. Double-sided polypassivation and polyfinger structures were analyzed to explore optimization paths. The chart below shows the preparation process of the double-sided poly structure and its optimization strategy outlook. First, it introduced a tunneling oxide layer plus polysilicon layer structure on both sides to reduce front-side recombination loss. Then, it applied local polysilicon passivation to reduce parasitic absorption, which is the polyfinger structure we mentioned. Furthermore, it applied the double-sided polyfinger structure to further reduce non-contact areas, and then used double-sided AR, anti-reflective coating, to further enhance passivation performance. The polyfinger structure mainly achieves local tunneling oxide layer plus polysilicon layer passivation contact in metallization areas, while non-metallized areas are passivated by double-sided aluminum oxide. Finally, LiCo is included to reduce metal-induced recombination. In actual industrial routes, the sequence is slightly adjusted. The introduction of LiCo technology was relatively early, while the development of double-sided polyfinger was relatively lagging. Based on the entire technology route, if the double-sided polyfinger structure is combined with platform-based BC technology, it can naturally evolve into TBC, TOPCon, back contact technology, achieving dual improvements in passivation and optical performance. TBC, as a fusion of TOPCon passivation technology and BC battery structure, combines the former's excellent passivation contact capability and the latter's advantage of no front-side shading due to all electrodes being on the back. It is a natural extension of the current industrialization route. The chart below shows the schematic diagrams of IBC, HBC, TBC, and doping-free BC structures, as well as efficiency evolution. It can be seen that regardless of the BC technology type, the main characteristics are no shading on the front side and an interdigitated back contact structure with selective transport layers for electrons and holes. The front side having zero shading and no doping layer can maximize optical absorption. The interdigitated electrode design and optimized stack coating can minimize electrical losses, achieving efficiency superposition. As a platform technology, it has strong industrial compatibility and can be upgraded based on mainstream TOPCon production capacity with good technological extensibility. Throughout this process, the precise patterning of the backside is the core of manufacturing. This creates a definitive demand for ultra-fast, high-precision laser equipment. Part 3. Solutions. I will focus on Laplace's process solutions and equipment status in laser etching. First, in the N-type high-efficiency PV cell efficiency enhancement path. Whether realizing the TOPCon polyfinger local passivation structure or constructing the precise interdigitated electrodes on the back of BC cells, the basic blueprint points to a common core requirement for mass production: how to carve complex film structures on silicon wafers with micron-level precision and near-zero damage. Laser technology matches this application perfectly. First, regarding precision matching. Through high-performance beam shaping and motion control, laser technology can achieve micron to sub-micron patterning precision, offering an optimal mass production solution that meets speed and cost requirements. The image on the left shows the microscopic morphology of a laser-etched sample. It can be seen that it achieves micron-level patterning, precision, and sub-micron etching depth requirements, with sharp steps between the laser and non-laser areas. Regarding damage characteristics, using short wavelength ultra-fast lasers, energy is applied to the film layer in an extremely short time, producing almost no thermal diffusion. Combined with wet removal of laser-induced damage, it ensures the efficacy of the core passivation layer. This can be seen in the relationship between thermal diffusion length and pulse width, and optical penetration depth and wavelength in the charts below. When we use short wavelength lasers, such as 532 nanometers, green light, or even 355 nanometers UV, we can compress the optical penetration depth to within a few microns or even tens of nanometers, thereby minimizing laser-induced damage and confining the damage layer to the sample surface. From the relationship between pulse width and thermal diffusion length, in our laser etching applications, using picosecond pulse widths sub 10 ps ensures a shorter thermal diffusion length and minimizes laser damage. Regarding controllability, as a digitized flexible tool, laser technology offers simple and intuitive parameter control and processing effects, enhancing the flexibility of the patterning process and the speed of technological iteration. Regarding platform potential, the same laser platform can achieve patterning requirements for different battery technologies, film types, and application scenarios through different laser specifications and configurations. Regarding core process solutions, they are mainly divided into the TOPCon polythinning solution and the BC patterning solution. First, the TOPCon polythinning solution. It uses laser etching to selectively remove the polysilicon layer in non-contact areas on the back, reducing parasitic absorption and increasing short-circuit current density and conversion efficiency. The polythinning solution is perfectly compatible with existing TOPCon process flows. It only requires adding a laser etching step after the phosphorus diffusion process. From the battery structure diagram, it can be seen that the surface, PSG, phosphosilicate glass layer formed after phosphorus diffusion is used as the laser absorption layer. In the laser etching process, ultra-fast lasers are used to open the PSG mask in non-contact areas. Then, subsequent wet processes etch away the film structure under the laser area and remove the laser-induced layer, forming a patterned effect. After applying this process, mass production can achieve an increase in short-circuit current density. JSC is greater than or equal to 0.2 milliamperes per square centimeter. Conversion efficiency improvement is greater than 0.15%, and bifaciality improvement is greater than 4%. Regarding laser configuration, Laplace uses a unique 120W green picosecond laser combined with a customized rectangular spot shaping solution. Laser CT cycle time is saved by over 20%, offering industry-leading throughput. The two images on the left show the morphology and processing effect differences between square and rectangular spots. In our polythinning application, to achieve the expected line width, using a square spot solution usually requires splicing the square spot 2 to 3 times. Using the customized rectangular spot solution achieves the expected processing line width in a single pass. Reducing pattern splicing minimizes marking, jump delays, and travel time. At the same time, the high uniformity customized shaping solution achieves optimal spot overlap rates and production yield. In the diagram below, it can be seen that after laser processing and subsequent wet etching, we can form sharp edge steps with good consistency. Sharp edge definition reduces carrier recombination paths. Additionally, the unique 120W high-power laser provides high-power redundancy, ensuring long-term stable mass production. Regarding the BC patterning solution, laser technology with micron, submicron precision, and ultra-low thermal damage processing achieves precise P-region and N-region patterning and uniform gap areas on the back of BC cells, ensuring excellent electrical isolation and carrier collection efficiency. From the overall battery process flow, laser patterning 1 and laser patterning 2 are mainly after the battery boron diffusion and phosphorus diffusion processes. They also use the surface, BSG, borosilicate glass, and PSG layers as laser absorption layers. From the battery structure diagram, patterning 1 uses BSG as a mask and uses UV picosecond lasers to open the partition patterns. In the patterning 2 process, green picosecond lasers are used on the stacked film to open the BSG layer to complete the P region and gap area preparation. The 2 images on the right show the overall precision of patterning 1 and patterning 2. From mass production data, Laplace's laser solution features typical pattern precision of plus or minus 10 micrometers, alignment precision of plus or minus 5 micrometers, line width consistency of plus or minus 7.5 micrometers, and isolation zone consistency of plus or minus 15 micrometers. Regarding laser configuration, Laplace has both green light and UV shaping solutions to adapt to different battery film opening needs. Meanwhile, self-developed dynamic laser precision control technology achieves the optimal match between pattern, precision, and marking speed. The image on the left shows our green light and UV shape spot shapes. It can be seen that both shaping solutions have good internal spot uniformity and ensure good processing consistency within the field of view. Simultaneously, Laplace can provide a dual UV picosecond solution. Compared to the green picosecond solution, the overall conversion efficiency improvement can reach over 0.15%. The UV picosecond solution can provide 80 W of UV power, maximizing marking speed and shortening process time by 15%. Regarding control, collaborative control of intelligent precision and speed enables the optimal release of the laser system's overall performance. Regarding engineering realization, Laplace can provide mass production level laser etching equipment. Its main highlights lie in incorporating the aforementioned short wavelength ultra-fast laser technology and freely matching optical components to ensure globally consistent output, guaranteeing ultimate overall process effects. In terms of capacity design, excellent process solutions synergized with automation cycle times can achieve a capacity of is greater than or equal to 10,000 wafers per hour in TOP-Con polythinning applications. In BC patterning, it can achieve a capacity of is greater than or equal to 4,500 WPH. Increasing single machine capacity reduces the quantity of equipment required per GW, thereby lowering the investment cost per GW. Regarding precision, the process section uses granite platforms and optical cavities. Coupled with high-precision CCD vision systems and inline AOI, automated optical inspection, systematic precision is ensured. Regarding reliability, equipped with an independent high-efficiency dust removal system. Regarding design, dual-lane independent and modular design, equipped with intelligent monitoring and predictive maintenance, ensuring reliability throughout the life cycle. Regarding capability panorama, Laplace provides complete support from process to service. Based on our deep understanding of battery processes and laser processes, we offer full process capability, support from lab verification to mass production ramp-up. We are not just an equipment supplier, but a process partner. The image on the bottom left shows the simulation optimization of process effects in TOP-Con polythinning. Through simulation optimization, we can clarify its efficiency, enhancement mechanism, and the source of electrical performance gains, and predict optimal polyfinger width, spacing, etc., and quantify the impact of other process indicators. Looking at the technological route layout, Laplace has always closely followed the trend of battery technology development. Our laser technology layout includes early SE technology, laser-induced metallization technology, half-cut and section hardening technology, polyfinger technology, laser edge isolation, and patterning technology in BC. Our laser process reserves are synchronized with the evolution of battery technology routes. Regarding laser configuration, we provide solutions ranging from UV to infrared, femtosecond to continuous wave lasers and their applications. We possess a full-chain laser solution capability from the laboratory to offline machines and inline production lines. Part 4. Laplace Company Introduction. Laplace is a leading provider of core process equipment and solutions for high-efficiency PV cells. Our main business involves the R&D, production and sales of high-performance thermal processes, coating, laser, and supporting automation equipment required for PV cell manufacturing. We also provide customers with semiconductor discrete device equipment and supporting products and services. The company is committed to enhancing innovation capabilities, cultivating creativity, and continuously assisting the development of the PV industry. We have technical reserves and forward-looking layouts ranging from monocrystalline to polycrystalline, PERC and PERC Plus, TOPCon, BC, and HJT, as well as future perovskite tandem cells. Regarding business segments, the company has 6 major bases and business divisions, including Shenzhen and Wuxi. Main equipment includes PV equipment, automation equipment, laser equipment, semiconductor equipment, etc. And we provide core process development and components. Company industry highlights. Using boron trichloride as a gaseous boron source, we were the first to break through the global mass production challenge of boron diffusion. We pioneered the development of small boat loading methods, improving yield by about 1% and saving costs by over 20%. Since its inception, Laplace is focused on the mass production challenges of N-type batteries. We were the first to develop several core equipment to break through the process bottlenecks of N-type battery mass production, including innovative low-pressure horizontal boron diffusion technology, PV-grade high-capacity LPCVD technology, thermal field technology and its heating, temperature control, and new quartz tube coating technology. The company will continue to deepen underlying core technologies such as heat, gas, electricity, and light, actively supporting every round of PV battery technological progress. In the TOPCon route, we were the first to help leading customers achieve large-scale mass production of the TOPCon route. In the industry, we pioneered breaking through the equipment technology bottleneck for N-type batteries, promoting the implementation and mass production of N-type battery boron diffusion and LPCVD equipment. In TOPCon technology upgrades, we were the first to support downstream TOPCon Plus technology upgrades and iterations. Downstream module efficiency further broke through 23.5% and power reached 635 W. Simultaneously, we developed core process equipment such as edge passivation lasers and polythinning equipment to further improve battery conversion efficiency. In the BC battery route, we were the first to help leading customers achieve large-scale mass production of technology routes like HPBC and ABC, continuously promoting BC technology upgrades. Downstream module efficiency continues to rise to 24.4%. And power reaches 660 W. The mass-produced BC battery processes generally adopt the company's LPCVD solution for the preparation of tunneling plus doped polysilicon layers. In perovskite and tandem batteries, we are actively laying out core process equipment required for different technologies, developing core vacuum process equipment suitable for perovskite batteries, and promoting the development of megawatt-level perovskite crystalline silicon tandem battery core equipment, and complete pilot line technology. The company's mission is to promote new energy technology, innovation, and benefit mankind, contributing to the dual carbon strategy and global energy transition. By the end of 2025, the annual production capacity of PV cell production lines equipped with Laplace process equipment in operation exceeded 500 gigawatts. Regarding operational layout, the company has 6 major R&D centers, 4 major production centers, and 3 major customer service centers, forming a location advantage with multi-point layout. In terms of R&D and technology, R&D and technical support personnel account for more than 50% of total employees. Regarding core technology and R&D team, the R&D personnel background covers multiple disciplines involved in the company's core product development, with a reasonable hierarchy and gradient, effectively supporting the research and development of process design, product, software, components, and core materials. That concludes the entire content of the report sharing. Thank you all for listening. Finally, on behalf of Laplace, I wish everyone a Happy New Year in advance.